Till now it will be silent there. I'm sorry about it. Yeah. It's recording now. Yeah. Hope it records from now onwards. Okay. So GBL, locally compact. You don't worry about the topological factor because we are going to work with countable discrete group, okay, locally compact. Hausdorff, okay, Hausdorff group. Okay. Then we will not prove this. Okay, this is measure theory. Then there exists a measure. There exists a measure which is called R measure. Okay. It's a generalization of Lebesgue measure. On R, you have Lebesgue measure, which is translation invariant. So you have that same property is satisfied. I write it for integrals, okay, such that f of st d mu t equal to integral f of, it's unique actually, unique up to scalar. Lebesgue measure is unique up to scalar. Okay. F of t d is ut. There exists a measure which, if you make a change of variable for translation, then this preserved. Okay. This is for all S in G, for all F in L1G. Whatever, whenever it's, of course, it has to be integrable. Okay. For all L1G. Okay. Okay. Now, this is just something we have to notice. Okay. So now for G in, let me not use G, let me use the same ST, because G and F I want to use the functions. So for S, for T in G, we have a locally compact Hausdorff group. For T in G, define, this is what is called shift, ut of F. I mean, for us, the Hilbert space H is L2G, okay? H is equal to L2G. Okay. Now you define ut for T in G. You define ut in B of L2G. We will prove that it's bounded. We will prove it's unitary, so it's bounded. Define ut in B of L2G such that ut acting on F at S I have to define, right? So you take a function in L2G and I apply UTF and at S I have to define. So this is for some reason I write it F of T inverse S. Some reason it is natural to write F of T S here. And I mean, then only it will be a representation. I mean, if you want UST equal to US times UT, the right way to define is T here. But for later computation, it will be easier if I put a T inverse here. It will be clear why I am doing this. Okay. So for that reason, but I mean, it is just the same thing with the product is you can work with the opposite product. Okay. It doesn't matter. If you have a G, you define the product in the opposite way, that will also give you a group, right? So that doesn't matter. Okay. It will be an opposite representation. That's all. So for some reason, I'm putting an inverse there. Okay. Then maybe I will not write this, define ut, we'll prove here. Then ut is unitary. It's a unitary operator for all t. So to prove that it's a unitary operator, we have to check it preserves inner product and it's surjective, or we have to prove it's invertible. Okay, that's what you have to prove. So UTF, UTG, okay, for F1G in L2G. We compute this. you know, the L2 inner product, you know that this is G UTF, which is a function at S, and UTG, which is a function at S, Q mu S, right? And mu is a Haar measure, okay? So this is equal to integral over G. I'm just writing the left UTF, UTG. The inner product on L2 is FG bar, right? So bar. Okay. Inner product of F and G in L2. Okay. We take L2 and where inner product between F and G is integral FG bar dV. Okay. That is the inner product in L2. So UTF is a function, UTG is a function, the inner product is this. Okay, d mu s. But then this is equal to F of T inverse S, G of T inverse S bar d mu S. Okay? But then this is T is some fixed thing. You can take it out. Okay? That works for any function. Okay? This is L2, this is L2, the product is in L1. Okay? If you take two L2 function, then the product is, point-wise product is in L1. This is like Cauchy-Schwarz inequality, which is proved in measure theory class. Must have been proved in measure theory class. So this is equal to integral over G F of T, G F of S, G of S bar d mu, okay, which is equal to F and G. So it preserves inner product. So this UT we have defined, which is shifting by T inverse. That is a isometry, okay, that preserves inner product. Now, UTFG equal to integral F of T inverse S, G of S bar dV S, right? By definition. Okay? I'm just taking UTF G inverse. Okay? This is equal to integral over integral of you change the variable. Okay? You call it F of R, where R is equal to T inverse S. So S is equal to TR. Okay? F of R. Then G of R is equal to S is equal to TR. Okay? TR d mu. And I mean, it is with respect to this, it is the same thing you can put, because you can put d mu r. Okay? You don't have to worry. When you change this variable, it's going to preserve. The measure is the same measure because it's translation invariant. Okay. So now this is equal to F, and here I have written T. So this is UT inverse of G. This is true for all F and G in L2. Okay. So this implies this equation. This is inner product equation. This implies UT star is equal to UT inverse. So we have proved that UT preserves inner product and UT star is UT inverse. Okay. This implies, I mean, it's enough if we prove it's I mean, it is one of the conditions for unitaries. UT star equal to UT inverse. Yeah, UT star equal to UT inverse, which implies if you want UT star equal to 1 equal to UT. I mean, TT inverse, if we just apply its identity, right? UT inverse, this is actually equal to UT star equal to UT inverse. This is equal to UT inverse. You want. Okay? I mean, we have it's not needed. It's enough to prove it's invertible. The UT inverse will give the inverse if you just look at it. Okay? UT is defined like this. UT inverse will multiply by T, that gives the inverse anyway. So UT is unitary. Okay. Now we have a collection of unitaries associated with, this is actually anti-representation of G is represented in this. It will preserve the product also. Okay. So now define lambda of G equal to, you take all these UT, T in G, you take the double complement. That's all. You just take the double complement. But this is equal to algebra generated by UT, PNP, and take the strong closure, right? By the fundamental, it's a strong closure. But the algebra generated by this is just the span of this, if you just look at it. Because USUT is UST, I mean, not ST, UTS. Okay? US times UT equal to UTS, right? So because of that, it is again U of something, okay, which will be one of these elements. So it will be just span of this UT. You don't need to take products. Product will give another element here. So T and G. Okay, then you take the closure and strong closure. This is very nice. Otherwise, algebra generated, you have to take the product and take the star. Star is also contained in this. UT star is there. So this is already a star algebra generated. I mean, you have to take the star algebra generated by that and take the strong closure. I mean, you have to take the star algebra, which is just the span. Okay, so span of this UT closure. So lambda G is just the span of UT this. So we want to discuss this phenomenon algebra, how it looks, and we want to prove that this gives rise to a factor. And the factor is not everything B of L2G. If it is B of L2G is a phenomenon algebra. So we want to get a non-trivial such thing. Our examples are finite dimensional algebra or B of H for some H or L infinity. Some L infinity embedded, represented in something. So we want to get first example, we want to get an example which is neither B of H nor some trivial finite dimensional algebra nor a B. Okay, that's what we want to prove. We want to get a factor which is not B of H. Okay. So that is our aim. Okay, for that we want to determine how this looks. We want to study this. Okay, so what is the first statement? We want to make some. Okay, this is I have given another one assignment. You look at another assignment. Assignment 2 in this class. I have given earlier some assignment. This is assignment 2 in this class. So G is finite group. Okay. Then it is just span of this UT, right? So consider this maybe not a general group for Zn plus the Zn plus. So this is an abelian group. Okay. So maybe I just give you the 3. This is 4 element, no? 4 element group. Huh? What? 3 element or 4 element? 0, 1, 2, 3. Okay, 0, 1, 2. So okay. I mean, I want 0, 1, 2, 3 or 0, 1, 2, 4. Up Z4. Okay, 0, 1, 2, 3. The 4 element group. So you see that this is span of these things. And they will be, you can prove that they are linearly independent. So the dimension of this, I mean, for when finitely, when you take a finite group, then the dimension will be the order of the group, dimension of this algebra. Okay. So for compute, I mean, describe or compute lambda of this. For G equal to this lambda. Okay. It will look like this. I mean, these are all just permutation matrices. You take all the, for Zn, it will be permutation matrix, just a span of permutation matrix. Just write it down, that's all. Okay, there is nothing. Just you understand that or something. For those who hasn't come to the class also, they can do this. I think it will look like this. A, B, C, D, and then D, A, B, C. It will look like all those things. Yeah, C, D, A, B, and B, C, D, A, right? It will look like this. Okay. We can, I mean, this is an abelian algebra and this has dimension 4. It will look like this. Okay. You can write it as actually C direction in some way. C, 4 direction of 4 copies of C. Well, if you can describe for some nice finite dimensional group, then try that. Okay? You can write more on your non-commutative groups. Okay. So if you have any operator on MNC is given by a matrix, any operator on a B of H can be represented by a matrix. It need not be the case that represented by an infinite matrix. It need not be the case that every infinite matrix will give rise to an operator. I mean, it has to be bounded. That's the only condition. If it is bounded, it will give rise to an operator. Okay, that need not be the case. So it will give rise to an unbounded operator under with some domain or something. So any operator on any infinite dimensional Hilbert space will be given by an infinite matrix. So notice that. So we are considering our H is equal to L2G. Okay. Let G be a countable group. G be countable. Okay. That's the only condition. Countable means it's like a small L2G. If you wish, let's put small L2G. Okay. The measure is just counting measure. G be countable. Then EG, this is a function. ET at S equal to F and T. Okay. Then if then ET T in G is an orthonormal basis. This is clear. In L2, I'm just taking one at the nth place, one at the tth place, everywhere else 0. Okay. Ortho normal basis. Okay. This is O and B. Okay. ETS equal to this. Now let's see how SMG or TMG UT acting on ES. This is a vector, this is an operator. Okay. ES at R equal to ES at TR inverse, right? Which is equal to delta of S TR inverse. We are using S here, okay? TR inverse. So, which is same as delta of T inverse, T inverse of T ESR equal to ES of T inverse R. Sorry, T inverse R, that's what we defined. I mean, that is why I defined T inverse there. I use T inverse because I want to get this relation. Okay. This is equal to delta ESR. Okay. This is equal to ETS at R as functions. This is as function ETS at R is equal to delta TS at R. This is a function. This is a ETS is a function. TS is fixed here, and R is a variable, functional variable. So ETS at R equal to delta TS at R, which is equal to this is equal to this. This is just numbers. Okay. So all these things imply that UT acting on ES equal to ETS. I want to get this relationship. Otherwise, I will get inverse here. Okay. If I define it through other way, I will get an inverse here. So that is why. So we know how this unitaries acts on the orthonormal basis. Of course, it takes orthonormal basis to orthonormal. It just shifts the orthonormal basis. Yeah, ES, the member of the orthonormal basis, it go to TS. It just shifts. It is like permutation. It permutes the orthonormal. Okay. Okay. Now proposition. X is in lambda of G. then let X ST SMP in G be the infinite matrix, be the matrix representative of X. That is, XST is equal to, if you think about it, and if you don't know, you just write it down and compute, which is just XET ES. Okay? If you want to represent a matrix with respect to orthonormal basis, these entries are given by this. This becomes, this is not XESET, because in mathematics, we have defined the inner product that way. In physics, it will be the other way. It will be nice. Okay? Yeah. Physics always, this will be the, this is how it will be represented. Okay. I think it will be ESEXET. There also it will be like that. Anyway, doesn't matter. XST is this. Okay. So if XST, so we will work with this matrix. We want to determine the matrix representation of operators in lambda G. Okay. This is just the, this is not unitary. This is in the algebra lambda G. So X is in lambda G. Then XST looks like this. Okay. This is just the what we are assuming. Okay. This is the, let this be the matrix representation. Then X ST equal to X S prime T prime if ST inverse equal to S prime T prime inverse. Okay. Okay, this is the condition. The entries at ST and S prime T prime. Okay. I mean, see, this cannot be, the lambda G cannot have the dimension of, I mean, in the finite dimensional. It will be infinite dimensional, everything infinite dimensional here. If we take the finite dimensional one, if G is of order n, this algebra lambda G will also have dimension n. It will be inside Mn, which is of dimension n square, but this will be of n. So there should be some relationship among the matrix entries. And that relationship, to get the dimension n, this is the relationship. Okay, this will make the dimension to be, I mean, square root of that. But here everything is infinity, so so first notice for P in G, UT is an operator that has a matrix representation ST equal to UT of S prime T prime if ST inverse equal to S prime T prime inverse. Okay. For UT, this is satisfied. Okay. That is, this is equal to UT. I'm sorry. This is UT, no? So SS prime, UR, okay? R for R in G. T is coming here also. So it should be UR. So this entry is UR, ET, inner product with ES, right? This entry is UR, ET, ES. Okay, this is the matrix representation. Now, this is equal to ERT, ES. This is equal to, of course, delta. These are orthonormal basis. Delta RT equal to S. This is equal to delta of R ST inverse. Okay. Okay. So if ST inverse is equal to S prime T prime inverse, they will be same R. They will have the same R. So they will have the 1 and the same place. Okay. So ut satisfies this, call this condition, or this condition. Call this a star. Okay. Then ut T in G, ut satisfies star. Okay. That is ut satisfies, I mean UR satisfies the UR. Okay. That is UR of E T E S equal to UR of E T prime E S prime. Okay. If S T prime T inverse equal to S prime T prime inverse. Okay. It satisfies this condition. That is a star condition. I mean, written in terms of inner product. So you can put a summation over R. So this implies summation over R, CR, UR, ET, ES equal to summation over R, finite sum. Okay, finite sum. Finite sum. Summation over R, CR, UR. You can take infinite sum also, but it should be well defined. That's all. Okay, CR, UR. I mean, you can take the infinite sum inside the inner product, but that has to be well defined as an operator. Okay, CR, UR. So this acting on ET, ES. ET prime, ES, if TS inverse is equal to T prime, S prime inverse. Okay. This condition is satisfied for the span. Span closure, you will take a, but this is a, I mean, this is a weakly closed algebra, right? So, a phenomenal algebra is weakly closed, not just star closed, it's strongly closed, it's weakly closed also. So if X lambda satisfies this condition, if X lambda ET ES equal to X lambda ET prime ES prime for all T S inverse equal to T prime S prime inverse, and X lambda converges to X weakly. Okay. And if, of course, if it is converges strongly also, it will converge weakly. So you don't have to worry about it. Okay. Then XET ES is equal to XET prime ES prime. Okay. This is satisfied for all TS inverse is equal to T prime S prime inverse. Okay. That's all. Hence the proof. Hence every X satisfies that because the weak closure is that, so it's satisfied. Because all these unitary satisfies this condition, linear combinations satisfy this condition, and the closure should also satisfy this condition because this condition is a weakly continuous condition. Okay, so I hope you remember weak topology. This is operator weak topology. Okay. Okay. Proposition. Shall I give it as an assignment? Anyway, I will do it. So let X is in lambda of G. Okay. No, I don't want to do that first. I'll do it next. What I want to do is let M equal to all those X in B of L to G, such that there exists a function, there exists a C from P from G to C, such that X of ST, this is a metric representation, X of ST equal to C of ST inverse. Okay. The matrix element is given by one function. So this makes it, I mean, this is given by a function, and these kind of functions are the dimension of G. I mean, they are given by functions on G. Okay. Matrix are functions on G cross G. This is just given by a function. These operators are determined by a function on G. Okay. All those X, which are bounded operators, such that the matrix entries are given by this condition. Okay. So claim that M is a one-dimensional algebra. Okay. Proof. Clearly, M is a vector space. Okay. If X is given by C, X1 is given by C1, X2 is given by C2, then this is just the matrix entry. Okay, X1 plus X2, the matrix will be added, and that will be given plus C1 plus C2. Similarly, lambda times X is also there. So clearly, M is a vector space. Okay. M is also an algebra because if X is in XY, X1, X2 in M, given by C1 and C2 are functions from G to C. Okay. We have two functions, C1 and G2. Okay. Then we want to consider the product of X1 and X2. Okay. It is just a matrix product, except it is infinite. Okay. X1, X2 at ST equal to summation X1 at summation over R, X1 of SR, X2 of RT, right? So this is equal to summation over R, C1 of SR inverse, okay, and C2 of RT inverse, right? I'm just saying this is a vector space. And then I want to prove that it is also an algebra. To prove it's an algebra, I take two elements, X1 and X2. Okay, then X1 and X2, the product I'm taking. I'm just computing a matrix element. X1 and 2 DST, yes. Okay. Now X1 is given by C1, X2 is given by C2. Then X1, X2, I'm taking the product. I'm just writing it like this. Now, I want to write it as one product. See, this shift is a permutation. Okay, this kind of SR inverse. This will run, if R runs through G, R inverse will also run through G. Okay, SR inverse for a fixed X will also run through G. Okay, because of the group. Okay, because everything is invertible and the property. So now I want to write it as one element. Maybe SR inverse. I try this. SR inverse to be STR L. Okay, let's call it L. Okay, L is in G. RSTUEW. Okay. L. Okay. There is no other right letter, I think. L will be usually index. Okay. UV will also, U we are using there. Okay, let it be L. Okay, SR equal to L. Okay. Then we want to find this RT inverse. What is RT inverse? Then R in, not to make mistake, let us write it. R is equal to S inverse L, and R is equal to S L inverse. Okay, correct, no? So this implies RT, this implies this is equal to summation. This sum will run through G again. This L will also run through G, L and G. Okay, C1 of L, here SR inverse equal to L, and C2 of RT inverse. R is S, L inverse. Right, SL inverse, right, T inverse. S is coming. R is equal to S inverse T inverse. This is, I think it's okay. Yeah. Now this is equal to summation over L in G. Okay. C1 of L and C2 of Hmm? T inverse, yes, L inverse. Say it again. R should be. Oh, sorry. Yeah, R should be L inverse. That's a mistake. S in the L inverse. This is okay. Now it's okay. Good. Yeah, this is what I was thinking. L inverse, ST inverse. Okay, that's okay. I'm writing the same thing again. Okay. Okay. Now this is equal to C1 star C2 at ST inverse, where C1 star C2 at, I write it here, where C1 star C2 at S equal to summation C1 of S, C2 of L inverse S. Okay. Instead of S, I have to put a ST inverse. The matrix entry is computed like that, right? C1 of, the matrix entries is given by C of ST inverse. Okay, instead of ST inverse, I have to get the S here in the function. So C1 star C2 of S is equal to C1 S. C1 of S times C2 of, sorry, C1 of S. Sorry, here it should be, it should be, sorry. Where is L coming? L is sum, okay, correct. C1 of L, C2 of, L inverse, yes. Okay, this is okay? This is, this is okay. You can write it the other way also. You can put the inverse here and write it also. Both will be same, okay? Yeah, C1L, correct, thank you. So this is right, C1L, CU2, L inverse, yes. Yeah, okay? So this is the new function. And you have to prove that this works, it exists, right? You want to prove that. Okay, but that is true because of the following. And you have to prove that that summation works, right? Okay. For that, the following observation will help. So notice x of E1. One is the identity. Okay. One is the identity. X of E1 is just the function C. Right? X of E1 at T. What is X? Right? X of E1 equal to X E1 ET summation, right? For any function, this is the for so this will prove that C is actually in L2. Okay. So this is okay. X of E1 equal to this. Right. Now this is equal to C of so this is basically X of T1 acting on X of T1, the number times ET, right? X of T, this is a number. Okay, and this number is XT1, right? The entry T1. Okay, this is equal to C of T1 is T, C of T ET. Okay, and this is equal to C. This is vector. Okay, I've just written it, and to write it rigorously, I've written it correctly. I've written it correctly. Okay, XE1, a vector in L1. X is an operator, E1 is a vector E1 is the first element of E1 is the element corresponding to identity in the orthonormal basis. XE1, which can be written as expanded through orthonormal basis like this, and that is equal to, this is just a number, which is XT1 ET, which is by definition, because there exists a C, this is just C of T. C of T says a summation should be. Sorry, I forgot the summation. Okay, this is, sorry, now it's okay. Summation, I forgot the summation. XE1 summation over T expand through the orthonormal basis. This number is exactly this. That is equal to C of T by the definition. Okay, that is equal to ET. That is equal to C. So these things imply that. So I have written this I have verified. XE1 equal to C. So this is equal to, this is in L2G, right? Now if, I mean, when the operator is given by a C, it's automatically that C is in L2. Okay. Now if C1, C2 are in L2, L2G, then C1 star C2, whatever that summation, that is just, the summation exists. That will be in L1. That will be in L1. What is the proof? That will be L1, I know, but I'm just wondering about the proof. I mean, if you convolve to L2 elements, Yeah, I know. I'm just thinking about the proof. You know the proof? Yeah. Say, okay. C2 of, let's write it. Okay. T is equal to summation over L or R, whatever. R in G, C1 of T, C1 of R is, first element is R, C1 of summation over R. Okay, C1 of R and C2 of RT inverse. RT inverse, right? Is right? T inverse. No, sorry, R inverse T. Sorry. Okay. Now this will be, I mean, this will be a, we don't know to work about L1ness, but the point is this will be less than or equal to this mod of this. You take the mod of this, and this mod of this is less than or equal to C1 norm 2 for the time being. This is what we want, right? This is the quotient Schwarz inequality. This is a summing over something. This is a sum over that. Okay. And I mean, so this will be less than these two, C1, C2. Okay. So this will give a, this sum exists. That's what I want for the time being. Okay. C1 star C2 is, will also be in L1, will follow, because it's given by bounded operator, right? No, it need not be the case at C1 star C2. At least I don't, at least we haven't given a proof. C1 star C2, we want, see, when X1 is given by C1, X2 is given by C2, then the product X1, X2 is given by C1 star C2, number one. But then that is a bounded operator, because X1, X2 is a bounded operator, C1 star C2 should also be in L2 because of this condition. Okay. So that will be in L2 anyway. We just have to prove that this exists as a number. This is okay. That is because, I mean, this is absolutely summable. Okay. C1 star T2 is less than or equal to this. That is less than or equal to this. That is absolutely summable because of this Cauchy-Schwarz inequality. Because of that, this is well defined. Okay, that's what the infinite sum should be well defined. Okay. Yeah. Now this is fine. Okay. What have we proved? We have proved that all we are trying to prove is this M, which is given by all those X in B of L2, which are given by these functions. This forms a phenomenon algebra. That's what we want to prove. We have proved that, and it's star closed, we want to prove. So if X is given by C, then you can notice that X star, XST, X star of XT is equal to XTS bar, okay, which is equal to C of TS ST inverse ST inverse okay, of bar. So if XC is given by C, then X star is given by C, then X star is given by C bar of T inverse. Okay. This function. We can even define this, call this as C star if you want. Okay. Where C is the function which determines X, then X star is given by C T inverse bar by this function. Okay. So this shows that algebra which we have defined, that M we have defined, it's a star algebra. It's a vector space, it's algebra, it has product in that. All we have to prove is strongly closed. Okay. Strongly closed is follows because it is just a condition of inner product, right? This matrix entry is given by a function. Okay. We have XST. Okay. So we only need to prove. Okay. We will use strongly closed rather than weakly closed. Need to prove M is strongly closed. Okay. Strongly closed. So if X lambda converges to X strongly, we have to prove that X is also in M. Okay. And X lambda is in M. We have a net in M and X lambda converges to X. This implies X lambda E1 will converge to X E1, right? Okay, right? So this is a vector in L2, which is a function on G. So this function, and X will be determined by this function XE1. That's because the matrix entries will converge. If there is a strong convergence, there will be weak convergence. So the matrix entries are some inner products, right? Weak convergence means the inner product converges. So the weak matrix entries will converge. Matrix entries are given by C. That C converges in L2, right? In particular, they will converge pointwise. The matrix entries pointwise will converge, and that's what you will get. So we have proved that this M is a finite algebra. Okay. Do you have any problem? You think there is any problem? We want to prove that this M, what we have defined, M is all those operators which are determined by a single function, G, C. Okay. So if you have a X lambda converging to X strongly, each X lambda is given by some C lambda, let us say. Okay. That C lambda is nothing but X lambda acting on E1. Okay. Now this X lambda E1 will converge to XE1. Call this as C. Now this X will be determined by C because the matrix entries are convergent, because of weak convergence. Strong convergence will imply weak convergence, and because of weak convergence that will happen. Okay. So X is in. So this implies X is in. So this is what we wanted to prove. M is a finite algebra. Okay. Fine. Can I take more time? You look tired? Okay. No tired. Okay. I will stop with this. I want to prove that lambda G is exactly this. Okay. Then I will stop with this. So that will be a good point to stop. Tomorrow I will prove lambda G is not B of H. It is not B of H. It is not B, it doesn't look like B of H of something else. You can have some other B of H sitting inside something like that. I will introduce tensor product. And if you have, you can take tensor products of 2H tensor K. Okay. You can have one tensor B of K sitting inside this. Okay. It will not even look like that. I have to prove. It is not just B of H. This is also something like, this is something on B of K, basically. This is like B of K is embedded in this. See, our lambda G is not just whole of B of H. That is clear because it has to be given by, not all operators will be given by this kind of function. So it is clear. It's not whole of B of H is clear. It's a finite algebra we have proved, and it will not be whole of that. Once we prove that lambda G equal to that, then then it will be clear that it is not whole of B of H. Okay, where H is that L2G. That will be clear. but then it will not look like some image of B of K, some representation image of B of K. Okay, that is also not true. That we have to prove. That for that we have classified, we will divide phenomenal algebra, not phenomenal algebra, factors into 3 types. Okay, type 1, type 2, type 3. We will prove that this is not type 1. Okay, type 1 will be exactly like B of H. Okay, I mean, I hope this looks beautiful. Okay, this because this is beautiful because John Neumann was trying to prove there is something called Vedderman theorem for algebra. Any semi-simple, finite dimensional semi-simple algebra is direct sum of matrix algebras. Okay, Neumann was trying to prove this. But he proved that any phenomenal algebra is direct integral of factors. And you want to prove that any phenomenal algebra is actually direct sum of B of this kind of B of H, like a Vedderman theorem for phenomenal algebra. Then got into contradiction. It's not true. And he found a single 2-1 factor like this. Okay, 2-1 factor. I mean, factor which is it doesn't look like B of H. Okay, it shouldn't look like B of H. I mean, it's not even image of B of H in some way. Okay. So what do I want to prove next? I want to prove this proposition. I just want to prove lambda g is equal to m, where m is all those operators here. M is definition of m is here. All those x such that there exists a function c from G to C such that xst is given by this. Matrix L3s are given by this. Okay. Now we already know that proof. If x is in lambda g, then of course xe1. I mean, we already know that x is in lambda g, then xt equal to x s prime t prime if st inverse equal to s prime t prime inverse. Okay. So that gives, so if c is equal to x times e1, okay, then x is given by c, given by hc. I mean, with that condition. Okay. So this implies lambda g is contained in m. Okay, we want to prove m is contained in lambda g. Okay. For that, it's enough to prove. See, this is the nice thing about phenomenal algebra. So if you want to prove m is contained in lambda g, okay, you have to prove that you take an element in m and you have to prove this is here. But m is equal to m double commutant. M is a phenomenal algebra, we have proved. And lambda g is phenomenal by definition. We are defining it as double commutant. So this is also double commutant of something. It's enough to prove the commutant, the inclusion is the other way. It's enough to prove lambda g commutant. No. Yeah, it is enough to prove lambda g commutant is contained in m commutant. Okay, if m is contained in n, then n commutant will be contained in m commutant. Okay, for phenomenal algebras. Okay. So if we prove lambda g commutant is contained in m commutant, then m will be contained in lambda g. Okay. So we want to prove this. So if we take an element, so let y, let's call it x prime, is in lambda g commutant. Okay. Lambda g commutant means it's enough if it commutes with the generators. The generators are the ut. Okay. So we have an operator x prime which commutes with the generator ut. Then we have to prove that it actually commutes with anything in m. Okay. So let x is in m. We want to prove x prime equal to x prime x, right? That's what we want to prove. Then we are done. So that is, we want to prove x prime, or x prime x, let's see, x prime x e yes e t equal to x prime e s e t. Okay, for the orthonormal basis. Okay, it's enough to prove this. Okay, so now you use the definition that now x is in M. Okay, let x of st equal to c of st inverse. Okay, where c is given, x is given by c. X is in M means x is given by c. Okay, so xst equal to cst inverse. Then we apply this definition here. The nice thing to notice here is the following. So x is given by c. So x st inverse equal to x st is equal to c of st inverse. Okay, for all s and t in G. Notice x acting on es equal to summation c of e ut. Is that right? Let's write it. This is equal to summation as vectors. I'm writing as yeah, as vectors. X es equal to x es et. Okay, summation over et. Okay, right? This is just I'm expanding through orthonormal basis. Okay. Now this is equal to maybe I call it et. Call it e x e. Yeah. So this will be yes, and this will be t, and this will be yeah es. Yeah, this is okay. Es. Now this is equal to xst. Es summation over t. Summation over t. Okay. Now this is equal to summation over t in G x s t inverse es. I'm sorry, the s is in summation over is s. I mean, t is fixed here. Summation is over s. Okay. Sorry. This is c of st inverse. Yes, es. Now this is, you change the variable and it will be summation over s in G, c of s, e of st inverse. So st. Right? If you hit it by t, st. Correct? This is right. And change the variable st inverse, I'm putting it as yes. Then I have to change s to st, right? Is that right? Maybe I will put r. St inverse equal to r. Then s is equal to rt. So this will become r, this will become rt. So this is okay. Now this is equal to summation s in G, c of s, us, the us acting on et. Okay. Yeah. This is what I wanted to write. I don't remember what I wrote, but this is what I wanted to write. Okay. Okay. Now we want to verify this equation. Okay. This is a vector notation. This is just a vector. XET is equal to XCS times USET. This is a real equation. I mean, in vectors. Okay, the vectors in the Hilbert space. Now I apply this. I write instead of now x prime x. I mean, this one has to be careful because there's a mistake in one of the book. So we corrected it later. Because you cannot write excess. I mean, you don't have this summation C of S US. You don't actually have this. Not just as operators. I mean, of course, if it is an infinite sum, you have to write it and define it through some topology. It's not true with respect to any topology here, at least. Till now, we haven't proved. Okay. So this is just only acting on this vectors. It is like this. I mean, to prove that, I mean, these vectors are total vectors. So if you have something in relation, infinite summation on total vectors, but then you have to prove that these things are bounded. Then only it will hold for everything. Then only this will hold in strong topology. Not even in strong topology, we don't have it. For that, we have to prove that these things are bounded. Okay, bounded in norm, which we haven't proved at least. So this is only on ET we have this relation, and that is what we are using. Okay, so say it again. I am having this relation XET equal to summation C of S USET. XET. I am just having this X is equal to summation C of S US. Okay. When applied to ET. I may not have it on everywhere. That's what I'm saying. Or neither this is, I mean, everywhere means if I have this relation acting on everywhere means it's strong convergence. Or stronger versus norm convergence. We don't have any of those things. I'm only having it on ET. That's all. And I'm only using that. Okay. So now if I apply this, this is summation x prime, summation over S in G, C of S. This is a constant U, S, E, E, S. I have to use R. Okay. R. Okay. C of R, U of R, E, S, E, T. Okay. Of course, this is linear, continuous, and you can take the summation out, everything. This is equal to summation over R in G, C of R, and X prime. You can take the summation because inner product is continuous, linear, and all that. X prime UR ES ET. Now, this is equal to summation R in G, C of R. X commutes with UR. X prime is taken in lambda G commutant. We want to prove this. Lambda G commutant is contained in M commutant. That's what we want to prove. X is in lambda G commutant. So here we can UR X prime ES, okay, and ET, which you have it here. Okay, you can do this. Now you do the following. R in G. Now you take the CR here as CR bar. Okay. No, now you take the UR star here. Now this is equal to CR X prime ES UR star ET. Okay. Now that is equal to some inner product X prime ES summation C of R bar U R star ET. Okay. Now this is equal to some inner product of X bar ES summation over R, of course, R C of R inverse bar, and here I am taking it as U star R inverse. I'm just changing the index to R inverse. Okay. Okay. I'm just changing the index to R inverse, okay, on all these things, which is okay. Now this is precisely now U R inverse. I mean, see if something is given by the function C, then the the star, x is given by C, then x star is given by C R inverse bar. Okay, C R inverse bar. So this whole thing will be x bar acting on ET. Sorry, x star acting on ET. Okay. Just think about it, convince yourself. It's clear to me. So this is equal to, I have x prime ES bar x star acting on ET. This is equal to x bar x prime ES ET. Okay, this implies x prime equal to sorry x prime, yeah, x prime, right? This implies what? Huh? Hmm. This is what we want, no? We started with what? We started with x prime x. Because yeah, we started. So this is okay. Okay. So x prime x is equal to x prime. Yeah, this is okay. Which implies lambda g commutant is contained in M commutant. This implies M commutant is contained in, right? That is what we want to prove. No, lambda g commutant. We want to prove it is in M. Sorry. This implies lambda g commutant is contained in M commutant. Yeah, it commutes with something in M commutant. So M is contained in lambda g. What we want to prove? This implies M equal to lambda. Good. Okay. So this lambda g is precisely those M which are given by that functions. See, that's all. This is the simplest group von Neumann algebra. What you can actually take is, you can take a von Neumann algebra, you can add a group on that. You can do, there is something called semi-direct product in groups. You take it two groups. Direct product is direct product, just like any direct product, something cross something. Semi-direct product is something where there will be an action of one group on the other. Using that, you will define the semi-direct product, where the other group will sit as a normal subgroup. Okay? That's a semi-direct product. Like that, if you have an action means this group is represented as unitaries. I mean, group, not unitaries. The group is represented as automorphisms of this M, automorphism of M, which is a one-ninth function. I mean, it's an automorphism is a homomorphism, which is also bijection. Okay. And it will be automatically continuous. Okay. So if you have an automorphism on M, if it is represented such that the product is also preserved, then you can do what is called a cross product. If you have time, you will do it. This is the simplest case of that, where the other algebra just see. Okay. There is no algebra. This is exactly, the construction is same as the cross product construction. I mean, this is a trivial case where the group is acting on, say, C. Okay. So this is lambda. You take this lambda g and then take another von Neumann algebra, take it together and take the double commutant, then you can describe all these things in matrix product. That's a more general construction. This is the simplest construction. And this is for this group, I mean, countable group, discrete group. For continuous group, you can do using the locally compact thing you can do. Okay. And this I will prove tomorrow, next class, that this is not, this doesn't look like B of H. This is something non-trivial. That's one thing you'll prove. Okay. This theory is very beautiful and very vast. So if you can have the cross product construction and I mean, using, in fact, many nice von Neumann algebras, very complicated von Neumann algebras, you get it through the cross product. Okay. And there is something called duality. There is a Tomita-Takasaki theorem. There is some duality theorem, which we will not do. We will not have time to do all that. So it's, of course, it takes a lot of time and very difficult. So there is a very nice theory involving all these things.